This conference will now be recorded.
Hello everyone, and welcome to the Satellite Book Club seminar series. Title of our talk today is Coming Ashore in a New Era for Sea Level Observed from Space. Our speaker today is Eric Leuliette from NESDIS's Satellite Altimetry Laboratory Branch, and our facilitator today is Aaron Updike, meteorologist from NWS WFO Indianapolis. As usual, session is being recorded. We'll take Q&A after the presentation. Please post your questions in the chat. And also, we encourage you, as usual, to sign in with your full names when asking a question so we can follow up with you. Remember to check your spam folders, as some emails occasionally go into spam, and we want to stay in touch with you. So if you're not receiving the correspondence you expect, please let us know. Always looking for future presenters. Please contact Ashore Bowman and Emily Maddox of the Tower S team. And the training team can help create any training materials that might pull together training materials that might be available or any new materials that you need. Contact Brian Mata of the Training Center, and he can help with that. Thanks to the Tower West team, Kashad Bowman, Office of the Chief Learning Officer, GOZAR, JPSS, and our facilitator today, Aaron. A few words to introduce Eric before we begin. Eric is the branch chief of the Laboratory for Satellite Altimetry in the NESDIS Center for Satellite Applications and Research. And as the NOAA Jason, a Sentinel-6 program scientist and project scientist, he co-chairs the Ocean Surface Topography Science Team. His primary research interest is in understanding and monitoring sea level change. Eric, welcome to the Satellite Book Club, and please begin when you're ready.
Great. Thanks for that introduction. Thanks for the opportunity to talk about satellite radar altimetry and all the interesting new things that are going on. As a start, I want to say I'm going to be presenting a lot of the work from a lot of the people in our branch. I didn't get a chance to acknowledge all of them, but I'd be glad to follow up about any of these topics that I'll present fairly quickly today. If you go to the next slide. So partly just wanted to mark that then, even though we have about a 40-year unbroken record of sea level observations from satellites, including also wave heights and wind speeds, we've seen in the last 10 years especially a change in the instruments that we're now flying. And so we have quite a variety of different technologies, and that's opened up a whole new set of, in addition to improved observations of sea level and waves and winds, new applications for NOAA users and users in the Weather Service, particularly as we move forward with increased coverage and increased observations from other satellites and in situ observations. We have more blended and integrated products that I'll briefly mention. And we still have some challenges looking ahead. So spatial coverage has always been limited for satellite radar altimetry. We're in the midst of changing that, but there's still going to be some challenges to providing temporal sampling for all applications. So I'll go more into depth with that toward the end of the talk. So next slide, please. So I just want to start out with sort of, what are our end users? Who uses altimetry? And so we have a range of applications. The most critical users for near real-time observations are the wind and high wave measurements used primarily by the Weather Service, both at the Ocean Prediction Center and the National Hurricane Center. Sea level observations then are assimilated into operational models, both at Weather Service, Ocean Service, and external assimilation, say at JPL, several universities. The Australian Bureau of Meteorology also uses our sea level observations in their assimilation. One of the most critical applications for altimetry at NOAA is then its use for hurricane intensity forecasting, and I'll have a few slides to go over that in depth. At the other extreme of sort of the time span of observations, then we also provide climate observations, particularly of sea level rise, both globally and regionally. I assume a lot of our users, particularly also throughout Weather Service and the rest of NOAA, don't necessarily realize that altimetry is being a benefit to their applications. one of the most important downstream products from altimetry is that we help find ocean currents more accurately. So that goes into all sorts of things like rescue operations, oil spill monitoring, or other debris or emergency needs to know where the currents are. And I won't have time to discuss it. One of the more interesting things that you can do with altimetry is that's the best source to measure bathymetry throughout the globe, because we have such poor mapping of the ocean bottom. Most of it is inferred from the ocean surface measurements that we make from altimetry. So when you dive deep into Google Earth and see the ocean floor, most of the time you're seeing altimetry measurements. Next slide, please. So I just wanted to briefly discuss how the altimeter works and how we both get measurements of sea level and wave and wind heights out of it. So if we go to the next slide. So the basic principle of all the altimeters, whether we use a laser or a radar, is that we need to precisely know the altitude of the satellite at all times. So we need to know the orbit. And then using either ranging from radar or lasers onto the sea surface or a lake or river or even an ice surface, then we can figure out, based on some other reference, what the changes have been in sea level or water height. And at the same time, we're also able to measure the topography of the surface, so we can infer the wind speed and we can also measure wave heights. So we can go to the next slide. So as I mentioned at the beginning, at the moment, flying on orbit, we have 4 different types of technology. So one that's been basically unchanged, but except for incremental improvements, is what we now call conventional nadir radar altimetry. That's been around since the mid-70s. We have multiple satellites, including 2 that NOAA is a partner with, Jason 3 and Sentinel 6, that are flying. And a whole variety of other missions, principally from Europe, French-Indian collaborations, and China also flies these conventional altimeters. In the last 10 years or so, there's been an order of magnitude improvement, and we now call high resolution or sometimes delay Doppler or SAR-based altimetry. So where we get these measurement heights using a much higher repetition of the radar, which has really driven down the signal to noise ratio. And so we have several missions, including our own Sentinel 6, that operates with this new kind of radar. Launched, I'm sorry, I have the wrong date on there. Launched just last year is SWAT, which uses a new swath interferometry technology. And so we're looking very forward to getting the data from that, and I'll sort of end the talk talking about that technology. And then I didn't want to neglect that there is a laser-based LiDAR altimeter, ISAT-2. It operates over the oceans and over lakes and rivers, but it's primarily a cryosphere mission to measure ice height. So there on the right, we've had this series of what we call the reference missions that have overlapped one for the other for at least 6 months, where they are only 30 seconds apart and take measurements of the ocean at the same time. So we've been able to calibrate one mission to the next since 1992 for an unbroken climate record, particularly for sea level rise. You can go to the next slide. So for most applications, then, what's important is that we're only taking nadir measurements directly under the satellite. So that limits our coverage compared to GOES and JPSS and all the VIIRS, all the instruments that have always done swath measurements. So we depend then on having at least 4, if not now 6 or 7 nadir satellites operating all the time, so that we can try to see the mesoscale observations of the ocean with the sampling that we have from each satellite. So you can see as recently as 2015, we were only covering about 1/4 degree of the ocean every 10 days to about 50% coverage. So that was probably minimum acceptable to trace ocean heat content and currents and mesoscale phenomena. We're doing a little bit better now that we have about 6 or 7 satellites operating in different orbits. So the coverage is closer to about 80% over 10 days. Ideally, since a lot of things, a lot of fronts, a lot of fast moving phenomena, we want to cut that back to having great coverage over 3 days, not just 10. So even with 6 satellites, there's still things we miss. We can completely miss a tsunami, say, that would just go by too fast for us to observe. If you go to the next slide. So again, I just wanted to sort of describe graphically these two different forms. Our conventional altimetry, where we're limited by looking a long track along the nadir path of the satellite to a resolution of maybe 5 or 6 kilometers of sea level and wave heights. So that's why we call that low resolution mode. So we send about 2,000 radar pulses a second, an average over those 2,000 to drive the signal to noise down to get sea level and wave heights to weather service requirements. So we can click again. And this new technology that's now on Cryosats, Sentinel-3, and operational on Sentinel-3A, B, and the new Sentinel-6 mission, we now call high resolution because it uses a sort of a SAR scanning Doppler beam to make scans almost 10 times faster than conventional mode. So that's unlocked, and that primarily then drives down the signal to noise. So that's allowed us to sort of increase the resolution of observations by a factor of 10 to just a few hundred meters along track. So that's been a big focus of our group, is trying to study how to fully exploit this high resolution mode to get either better accuracy or even higher resolution. If you go to the next slide. So this sort of in a convergence of those two forms of radar. So the conventional modes were started with Topex Poseidon and continued up to Jason 3 that's still operating. In the meantime, Europe embarked on trying to develop this delayed SAR high rate, starting with Cryosat 2 over 10% of the ocean, and now globally on Sentinel-3. They don't work the same way, these two modes, because the Doppler scanning is slightly off nadir. It sees the wave and wind field slightly differently, so it's not exactly backward compatible. So Sentinel-6 was designed to operate in both modes to have backward compatibility for the climate record back to 1992. So that it operates both in the low resolution conventional mode and does the Doppler beam scanning, and we use the SAR techniques to get a more accurate. So that's why it's almost as if there's two satellites missions in one with Sentinel-6. So there are both high rate and low rate products for winds, waves, and sea level. So you go to the next slide. So I think it's worth, since many of you might be interested in the wind and wave measurements, just a little bit about how the radar actually interacts with the ocean surface. So again, in conventional altimetry, we send these 2,000 pulses a second, and then it starts as sort of just a chirped pulse in the red on the right. And then those wave fronts from the radar interact with the ocean waves. If you can click 1 or 2 more times, I think. Maybe just, yeah, several clicks. Sorry. How about like 3 more clicks? At least, yeah, well, there we go, thanks. So if you look over in the left where the top wave, the top radar wavefront hits the highest peaks of the waves, and that returns then the earliest signal back to the radar antenna on the satellite. And then as the next, still moving at the speed of light, but as that radar beam spreads out and hits then lower and lower waves, then more of the energy is returned over time. So in the bottom right, then we get this characteristic curve over most of the ocean where we start to see a ramp up of the returned energy and then a sort of a decline. So if you go to the next slide, then we use all that information about how the radar energy came back to find out what the average height of the ocean was. So that's sort of the midpoint there in green of where the energy returned. And so we measure the amount of time that took. But we also can measure what's the backscatter of the radar, the amount of scattering of the energy. And from that, we can infer the wind speed. And then if we measure the slope, that red slope there through the green dot, the steepness of that slope tells us the average wave height under the footprint of the satellite. So from each once per second averaging of those thousands of waveforms, we can get a value for wave height, sea surface height, and wind speed. I can go to the next slide. So, okay, my equation's missing a whole bunch of minus signs. But yeah, to get sea level is much more complicated for us than measuring the wind speed and the wave height. To get the wave heights, we just need to fit to that curve on the previous slide. To get sea level, we need to know the orbit very precisely, and we need to make a bunch of corrections, including how the radar goes through the atmosphere, and then subtract things out like the tides. There are onboard other instruments in addition to the radar that we use to correct in order to get the sea level measurements. And critically, the orbits are so important to getting the sea level measurements that there are 3 independent measuring instruments on board of most of the satellites in order to get the orbits precisely. And whereas that used to be the limiting factor in the accuracy, there's been tremendous progress. We used to know the orbits to tens of centimeters. For Sentinel-6, we now know the orbits to about 7 or 8 millimeters at any point. So out of 1,400 kilometers, we can measure the altitude of the satellite to the width of a pencil. I can go to the next slide. So then under different wind and wave conditions, then that curve of the returned energy changes. So this is a condition over the ocean where we had low waves and low winds. So in that case, the surface is very reflective. So much of the radar energy comes back, and it comes back fast. So that makes a steep slope in the return, which means low wave heights. And there's a very high peak to the curve, which means low winds, because much of the energy is reflecting back. It's not scattered. You can go to the next slide. So the different conditions, high waves and high winds, then there's much more scattering, so the peak is lower. And then the energy takes a longer time to come back from the earliest, highest waves to the lowest, the bigger range of wave heights. So that means then there's the steeper slope. So if you go to the next slide. So we have a variety of latencies to the products. So we try to get out the wind and waves. We don't need the orbits for. It's much simpler. We can produce those in 3 to 5 hours. And so those go directly onto forecast screens to AWIPS. Whereas for sea level, it takes a little longer to get everything processed more accurately. And so most of those measurements for data assimilation and for ocean heat content forecasting come from a product that's 1 to 2 days delayed. And then finally, then there's a climate capable product that, depending on the mission, takes 30 to 60 days in order for us to more accurately measure stable sea level so we can assess sea level rise. I can go to the next slide. So here's a snapshot where we have the global view of AWIPS, where we have, I think in this picture, there's maybe 6 of the altimeters operating. So this is the near real-time wave heights that were available at that, whatever date this was, when we had 6 satellites operating. So if we can go to the next slide. So these, can be overlaid. So if you look, this is a storm several years ago west of Ireland, where there were significantly high wave heights. Jason 2 measured 62-foot waves, and then overlaid, then you can see with Wave Watch 3. So that gives the ability to compare to either GOES-R imagery, scatterometry, Wave Watch 3. So both the Ocean Prediction Center and the National Hurricane Center can use these waves and winds to overlay over other observations. So many cases you would just get excellent agreement with the wave model. And the next slide is an example where, particularly in times when you have mixed conditions, where you have wind and wave in opposition, so strong winds that are opposing currents. There are cases then where Wave Watch 3 is not as accurately predicting the forecast condition. So you can see that then overlaid by the winds we were seeing from one of the altimeters. If you can go to the next slide. Right, so let me just in the last few minutes just run through some of our other current applications and then some of the research work with future applications that are coming. So you can go to the next slide. Many of our applications are that come from STAR are driven by our radar altimeter database system, and that's where we take all these different missions, all those different technologies, and we try to homogenize the data and have consistent products of sea level, wind, and wave, no matter what the mission. So data agnostic applications. So those range again from all the, that we provide data simulation to weather service and NOS. We're providing and have a project to make blended surface currents that would bring in sea surface temperatures to infer currents, including the GFS winds. We produce climate data sets. We provide those sea level, wind, and wave heights out through Coast Watch. There's an operational heat content product, and I'll briefly describe. Then we have a next generation replacement for that. And then we have some other products in development for eddy tracking and kinetic energy. And this is just, we also have a few more things in the works, but this is the ones I thought would be relevant to this audience. So next slide, please. So again, here we have, we provide for the State of the Climate report and on our website periodic updates of global and regional sea level rise. We also compare that to other in situ data from Argo and the GRACE gravity mission to try to close the sea level budget, which for the last 10 years with the independent observations, we have not been able to completely close that record, which is a big open question in the community. If you go to the next slide. Again, for one of the most important products is ocean heat content. On the left side of the picture, you can see during Hurricane Katrina, the intensification was much more visible in the altimetry because the surface temperatures from SST observations showed the whole Gulf essentially warm. The loop current is not visible in SST. The loop current is visible then in height due to the thermal expansion of the loop currents expression in terms of sea level. So the operational ocean heat content product blends SST and the altimetry to infer what the mixed layer depth is, and therefore what the amount of stored energy is in the loop current. And so you can see that when Katrina moved over that loop current that's visible in the altimetry, it's when it jumped from a 3 to a 5 storm. If you go to the next slide. And just click a couple more. So again, we have this, I'm sorry, one more back. So we have this operational product that covers 3 basins. We have one in development that would be global and would use more consistent input of data. It would also be available potentially along track for all those altimeters. So even at higher resolution, so if there was a need to see exactly where the fronts were for the loop current, say, or eddies, we have a more accurate representation of that. That's something that can even go on AWIPS. If you go to the next slide. So we have several interesting things. I'll just have to skip through a lot of this, but we have new algorithms that are in development at NOAA, particularly for these new forms of radar. If you go to the next slide. What was not understood when we started looking at this new delay Doppler over the wave heights was that the radar is sensitive to the vertical motion of the waves. So right now, the wave heights of Sentinel-6 for the high resolution product are not meeting the requirements because they don't account for this vertical motion of the wave height. So we've generated a correction. EUMETSAT will put that in place next year. And we've also developed a new processor that actually solves for the vertical wave velocities at the same time as the wave heights. And that's potentially something we could implement in the future. If you go to the next slide, and just click through to the, yep, sorry, I should have gotten rid of all these. Okay, so we've also found a way to actually use more of the information from the delay Doppler that allows us to focus. And even though delay Doppler in the baseline products has increased the resolution by a factor of 5 or so, we found a way to increase that resolution to a few meters, a factor of another 20 to 50 to 100, depending on the application. So if you click one more, so that we've been able to demonstrate by looking at very narrow canals. Let's, in the interest of time, just click one more. So over the Netherlands, there was a canal that one of the altimeters passed over that had ditches to the left and right. So with this technique where we focus the radar beams in processing, if you click one more slide, we were able to see that we can individually measure the water heights of the ditches that are just a few meters left and right of the main canal that's only 18 meters wide. So we were able to distinguish the land from the water and the height of each of those. So we've been able to demonstrate, and this will work over the ocean as well, that we can see down, instead of kilometers along track, we can see meters along track and find wave and winds and height. And you go to the next slide. In the same way, then we've been able to better measure leads among the sea ice because we can focus on the water in between the ice flows. And the next slide. But again, our limitation has been that as long as we're only seeing nadir, we can miss a lot of particularly small scale phenomena in the ocean. So the one way to solve that now, if you can go to the next slide. Yeah, here's just an illustration of that, you know, we can only see again when we pass over these lines in the ocean on the right. And those pass through only every 10 or 27 days, depending on the mission. So you can go to the next slide. So NASA and the French space agency CNES developed this new technique using an interferometer. So there's a 10-meter antenna that deployed in space. As long as that antenna doesn't flex more than a micron, just a fraction of a depth of a hair, then you can infer over a swath to the left and right of the satellite sea level. And so this mission was launched in December. It's still undergoing its commissioning. You go to the next slide. So NASA and CNES have released a handful of pictures. We're still, we've seen some CalVal data from this. We're still waiting for this to be released later this year. But this will, at least where we have these swath observations on the right, we'll have much higher resolution coverage. So finally, we'll be able to see submesoscale sea level variations. If you go to the next slide. The only caveat, or there's two caveats, is that this kind of mission needs frequent crossovers of the data to do its calibration. So the orbit was designed to densely sample parts of the ocean in rapidly so that they can get the CalVal data. So that means that every 21 days, you'll get very high resolution mesoscale observations. But as you can see in that slide on picture on the left, then there's a whole huge gap in the ocean where then you won't have any observations at all. So over 21 days, you'll have complete global coverage, and you'll have mesoscale when you have it. Also, because of the processing needed, there's no near real-time data for wind and wave. Yeah, so to deal with the fact that then one swath mission won't give us great coverage, the European Space Agency and EUMETSAT are looking at options that would both guarantee continuity with their set of operational satellites and would help solve this issue of not enough coverage. So they are considering 3 different solutions. One is to just use a constellation of small satellites that are similar to the ones we have up now. Another would be, I would call SWAT Light, a swath mission that would be cheaper and the ability to have 2 of those for greater coverage. And then the one I call, I don't know if it's the Goldilocks one, it's just right, or somewhere in between, where you would use 1 swath and then maybe another small constellation of conventional. So we can go to, I think, the last slide. So again, we have this unbroken record that should be at least 40 years long, with the new sets of technology that are on orbit. It's letting us see smaller scale phenomenon, opening up better observations along the coasts, polar oceans. We have more opportunities to blend with other observations. The temporal sampling of altimetry is still sort of the limitation that we have, but the agencies are working to address that in the next decade. So thank you.
All right, thank you so much, Eric, for that. That's some really great information. Just for everybody, please stay on the call for a discussion, including field forecast offices, regional headquarters. And then if you do ask questions in the chat, just please make sure you use your full name so that we know who you are. We can address you properly. There will be a feedback form that'll be posted in the chat room as well here shortly. Please share any feedback that you have with the Satellite Book Club and helps with improvements in the future if you have any. In next week's Satellite Book Club meeting, so that'll be Thursday, June 29th at noon Eastern Time, Eric O from the Tower S team will discuss features and capabilities of the Polar Planner tool. So tune in for that next week if you're interested. And then please contact the Tower S team, so be Kashad Bowman and Emily Maddox, for questions on the Satellite Book Club or for configuration of satellite products as well. So with that, we'll start the discussion here. I'm just going to do my quick question here, and then we'll get into some of the questions from chat. So Eric, what kind of temporal resolution would you need to properly forecast storm surge? And could you use some of because you said that it doesn't, actually cover the entire, ocean basin with one small pass through. Could you use just a small pass through if it happened to go through where a tropical cyclone is going to get storm surge data? Or do you think it's reasonable in the future to quicken up that process so it's not a 21 days to get the mesoscale features?
Yes, well, so that's why we're excited with SWAT, because then we should be able to see, we should get lucky and then observe storm surge, along the swath, which should give us good resolution. Again, lucky for us, but unlucky when there's storm surge. But we've gotten, there've been a few cases where we've seen storm surge just with the nadir ones. Hurricane Sandy, we were able to see and measure the surge. So there's enough there to try to do some validation of the surge models. That should be that then something like Sentinel-3 next generation will let us see storm surge nearly every time it happens.
All right, awesome. That's good to hear. And then one last question from me here. Is there a point near the coast where that thermal expansion-based sea surface temperature measurements becomes inaccurate, where it starts to just incorporate with, less ocean-based, boundary layer type or ocean layer interactions? Because things like I was, thinking about marine layers where cold ocean currents really have a big impact on those forecastings. Is there a point near the surface where you can't really use thermal expansion anymore?
Well, it is true that, as you get close to the coast, it's mostly the wind-driven changes that are what you're picking up and not really the thermal expansion, or it's hard to pull out. I had a few slides. We are limited, so as you get within 10 kilometers of the coast, okay, the altimeter doesn't, the altimeter areas start increasing and definitely by 2 kilometers within the coast, you can't really use the altimeter. But partly that's part of the issue with the coastal is, yes, it depends completely on the dynamics of the region. So some places are so salinity driven, that's mostly what you're seeing. There's in bays and inlets, of course, you're mostly got the dynamics of the wind driven currents going in and out.
All right, so now getting into some questions from the chat room, and I apologize to anyone if I mispronounce your name, but from Mark DeMaria, will the next generation of products to be able to estimate other subsurface ocean parameters besides OHC, such as the thermocline depth and ocean stability below the mixed layer?
So I answered in the chat, so yes, it should infer the thermocline depth. Some of the limitations are that we have to use a climatology to do that inference. So there are, you're limited by the accuracy of your climatology. We can check with the PI on that, Deirdre Byrne in my group. I don't know that we can infer much below the mixed layer depth. So the ocean stability, but we can ask.
All right. Another question from the chat room here. This is William Sweet. Eric, what would it take to use the eddy tracking capabilities to help predict coastal sea level anomalies? The East Coast could benefit from such information.
So it's in demonstration now. So it's mostly just time and money, I guess. Now, we're interested to see then what we can track with even higher resolution data. So at the moment, we're only trying to do quarter degree. So that gets the vast majority of all the large eddies. But we're not quite sure what the limitation is on the low small scale. And then there's some limitations about when an eddy, eddies that reform or split off, our tracking sometimes loses track of those or sees them as a different eddy. So we're trying to investigate some artificial intelligence ways to try to track the smaller eddies.
Okay. That's so far is it as far as what we have for the chat room. If anybody has any questions, please post that in the chat room. We'll get to them. But since we still have a couple more minutes, I'll get to a few questions that Brian had posted in here. Based on slide 15, can anything be done to speed up the generation delivery of NRT wind speed or wave height measurements?
Faster than 3 to 5 hours. At the major limitation on that is the data dumps to ground stations. So usually we only, we try to once per orbit roughly is when we do a data dump. So if the altimeters are designed to dump the data faster. Otherwise it's just computational speed.
Okay. All right. One last question here before we wrap up, again from Brian. On the Katrina case, where we saw a strengthening that was correlated with that loop current, a feature that we really couldn't see on the SST fields, have these findings been corroborated with other studies?
Yeah. Oh, yeah. There's a whole set of papers. And there's been some Aussies to try to demonstrate the value of altimetry toward hurricane intensity forecasting compared to all the other inputs to intensity forecasting.
All right, and one other question: are we able to incorporate that with models then too, with like boundary layer schemes to help with hurricane and tropical cyclone forecasting then?
Yes. So we have a project now with AOML to try to provide our long track estimates of the heat content. It's the data is assimilated into the models. Perhaps if we were including the heat content directly into the models, there'd be further improvement. So that's an open question.
Okay. All right. Thank you so much, Eric, for all those answers to those questions. From very interesting stuff.
Great, thank you.
All right, I'll pass it along here to Brian, and he'll finish up everything.
All right, thanks very much, Aaron, for your facilitation. And Eric, thanks very much for this talk on altimetry and its many applications. We're always interested in the near real-time data as well, so appreciate your feedback on that, and also the feedback on how near shore the retrievals can be done, which is really important, of course, for those coastal sites. So thanks for everyone for hanging in. Sorry for the minor disruption. We sometimes have that, but we only lost a few folks. Just a friendly reminder again, please join us a week from today with our next Satellite Book Club. We'll have another Eric. This time, Eric of the TOWRS team will be speaking to us about the polar planning tool. Look forward to seeing you again, and thanks for your participation. Everyone have a great day.